All right, guys, so for our final video in chapter 13, we're going to be solving trigonometric equations. Now, these are different from identities. They're going to look really similar when you're first looking at them, but big difference between equations and identities. Identities are true no matter what. It does not matter at all what you plug in for theta. Now, equations are only true sometimes, and so our job with this section is to figure out when those equations are true. So we're going to solve for certain values of theta that would make the equation true. All right, so first thing that I want to write up here is that we're going to be using this Pythagorean identity a lot. So it's good to remind ourselves of this. We're also going to be using the unit circle a lot. So I have one pulled up on my computer that I'm just going to like flash up on the screen when we need it. So this identity, we're going to be using it in its original form, but we're also going to be using it kind of manipulated around. Because of this, if I subtract sine squared from both sides, I also get this version, 1 minus sine squared. I could also take this and solve for this one by subtracting cosine squared. So the original is super important, but in the work that we're going to be doing today, these two are super important. So it's just taking this original Pythagorean identity and just manipulating it around. So when we are solving equations, this is an example right here. This is our first equation. We want to basically think of either sine or cosine as being our variable. So if we think of cosine as being like an x, think of sine as being like a y, we're trying to solve for either x or y. Problem with this one is that we've got a mix and match of variables here if we have both cosine and sine in the same equation. And we can't solve an equation when we have two different variables. So we need to do some sort of substitution. So what we're going to do is substitute this cosine squared. We're going to replace it with this right here, 1 minus sine squared. So that's the first thing I'm going to do. So make a little substitution. The 2 stays there, and I replace cosine squared with 1 minus sine squared. Minus 1 equals sine of theta. So now everything's just in terms of sine. So that's like we got it in terms of just one variable, which is a good thing. So I'm going to start by distributing this 2. And then what you want to do is you're going to solve by factoring, and factoring works the same as it does with normal variables. You want to get everything on one side and then solve by factoring. So since this is a negative, I'm going to put it over on the other side. So I'm going to add that 2 sine squared to the sine that was already here, and then 2 minus 1 is 1. So I'm going to subtract that 1 from both sides. So now I have just a 0 here, which is good. So here's something that I want you to keep in mind. This is really, really similar to just like a normal equation. So like say that we replaced this with just an x, it would look like this. And that's just an easy equation that I can factor down. So picture sine as being like a variable. Okay, so I still have 0 right here. This 2 sine of theta squared we're going to get by multiplying 2 sine of theta times sine of theta. So the factoring works the same way that it would if I was factoring something like this. So 2 times sine gives me this 2 sine squared. And then when I FOIL it out, I'm supposed to get negative 1 from these two right here. But I want to make sure I have positive sine in the middle. So 2 times positive 1 for the outside, combine that with 2 times negative 1 for the inside. So 2 sine minus sine, that gives me the 1 sine that I have in the middle, and this gives me the negative 1. So solve it just like when you're factoring. We're going to take each one of these and set them equal to 0 so that I can solve. Oops, forgot my little theta in there. So I'm taking both of these and setting them equal to 0. So here I'm going to add 1 and divide by 2, and I end up with this. Sine of theta equals 1/2. And then here, subtract 1, I end up with sine of theta equals 1. So I'm trying to solve for theta. This is sort of like the inverse stuff that we did. We want to know what angles have a sine of 1/2. We also want to know what angles have a sine of negative 1. Now look at our restricted domain here. We have to make sure that the only answers we're giving are answers that fall within that interval right here. So let's start with this. Let's start with angles that have a sine of 1/2. So let's look at the unit circle that I have on here for you. So only in this top part right here, because we only said between 0 and 180. So here's a sine of 1/2, because remember you're looking at the y value, and here's a sine of 1/2. So we would give 30 degrees, we would also give 150 degrees. That's the first part of our answer. And then let's see what else we get from this one. We want sine of theta to equal negative 1. Okay, so again, we're looking just at the top half of this circle. There is no negative 1 for my y values. It's down here, but that's not within my domain, so I actually don't include that at all. So my only answers that I have would be these answers. So that would be your final answer there. Okay, let's look at another one. And I promise these will get easier with practice. So here, this is in terms of cosine, this is in terms of sine. We're going to rewrite using this expression right here, 1 minus cosine theta. So let's start there. So instead of sine squared, I'm going to write it as 1 minus cosine. Okay, so we're going to start with that. All right, so let's add this all over to the other side. So we'll have a cosine squared plus cosine. And then I'm going to subtract that 1 from both sides. So I'll have 1/4 minus 1, which is -3/4 equals 0. Okay, so this gets a little bit tricky just because I'm dealing with fractions here. So we're going to make things a lot easier on ourselves if we multiply everything by 4. Okay, so multiply everything by 4. That way we can clear out that fraction. Okay, and then just like the one up above, we're going to solve by factoring. So if we start with this, this one we could either do 2 times 2, or we could do 4 times 1. So you could do just like a little guess and check sort of thing, or we could do like that different method where we expand this out and factor by grouping. So remember the method where we multiply 4 times -3, and that gives us -12. And then we're looking for two values that multiply to -12 and add to +4, and that would be 6 and -2. Okay, so that's what we're going to do. We're going to expand out. We're going to keep 4 cosine and expand out that middle term as 6 cosine theta minus 2 cosine theta. Okay, so now we can factor by grouping. So group these two together. They have a 2 and a cosine theta in common. And we're left with 2 cosine theta plus 3. Group these two together. All they have in common is a -1. And we're left with a 2 cosine theta plus 3. Okay, so our two factors. We have 2 cosine plus 3. And then once we factor that out, we're left with 2 cosine minus 1. Okay, so we're going to set these two equal to 0. So if I set this one equal to 0, I end up with cosine theta. If I subtract the 3 and then divide by 2, I end up with -3/2. And then this one, if I add the 1 and then divide by 2, I end up with 1/2. So we're looking for angles on the unit circle that have a cosine of -3/2 and a cosine of 1/2. So let's take a look. Okay, so cosine of -3/2, we are never going to find that anywhere on this unit circle. The very lowest value is -1. So you're never going to hit -3/2. That's too far over here. So that doesn't give us a solution. But then we have a cosine of 1/2, and that's going to happen here. It's going to happen here. And it's just going to repeat itself over and over and over again because I can keep going around the unit circle. So we have 60 and also 300. And then they just kind of repeat themselves. You could go around the unit circle over and over and over again, but those are the two that you get just on your first pass of the unit circle. All right. This one is a nice easy one. The curveball is that we have radians. So this one, theta is already almost by itself. I just need to divide both sides by 2. So I end up with sine theta equals -1/2, and I want to give that measurement in radians this time. So if I look for -1/2, that's going to happen right here, and it's also going to happen right here. I'm sorry, I'm looking at next values. Y values would be right here, and then right here. So that would be at 7 pi over 6 and 11 pi over 6, and then, you know, an infinite number of times after that, because this function is periodic. Okay, just in the interest of time here, we are going to skip over this problem and then move on to our last little topic here. So extraneous solutions, we've done extraneous solutions with many different types of equations. It is possible, of course, that you could solve an equation and then it turns out that you don't actually have any solutions for it. So this one, we've got sine times cosine is equal to cosine. This we're going to solve with a slightly different method. Start by subtracting this over to the other side. So I'm going to have cosine squared theta on the right side. Then I'm going to subtract sine times cosine. And then remember, technically when I moved this stuff, it left me just with 0. So I am going to factor this. I'm going to factor this one using a GCF. So that's a possibility for you as well. See, these both have a cosine. So I'm going to factor out a single copy of cosine and then write my leftovers. So when I factor out a cosine here, I am left with cosine minus, and then when I factor out a cosine here, I am left with sine. So those are my two factors. In solving, I am going to take these two factors and set them equal to 0. Okay, so starting with this one, I'm looking for a value of cosine that's equal to 0. Here's my restricted domain. Notice it's given in radians. You want to make sure your answers are also given in radians. So where's the x value equal to 0? That happens here, also happens here. So that would be pi over 2 and 3 pi over 2. There are two of your answers. And then here, I'm going to add sine over to both sides. So this is kind of an interesting one. This one means we want the cosine value to be equal to the sine value, which means we want the x and the y coordinates to be the same. So let's look where that happens. See, that happens right here. See how the sine and cosine are the same value. Doesn't quite happen here. Happens again here. And then again, doesn't quite happen there. So pi over 4 and 5 pi over 4, that happens again. Okay, so lots of solutions to this one right here. Okay, let's look at another problem here. Cosine is equal to 1 minus sine. All right, so this one is kind of a strange little one. It seems like there's really nowhere to go from here. So what we're gonna do, this might need to happen for a problem that you work on. We're gonna square both sides. Okay, so when we square this one, we end up with cosine squared. And then when we square the one on the right, we end up foiling it out. Okay, so we have 1 minus sine, oops, just sine, and then 1 minus sine. Okay, so this right-hand side, when I FOIL it out, I get 1 times 1, and then negative sine and another negative sine, so it ends up being negative 2 sine, and then plus sine squared. Okay, so since this is all in terms of sine, I'm going to do that same substitution that I did at the beginning of the video, where I can write cosine squared as 1 minus sine squared, and then rewrite everything over here. Okay. So because it's a quadratic, I'm going to solve by factoring, so I'm going to move everything over to the other side. So I'm going to subtract this one, and they will actually cancel from both sides, and then I'm going to add this sine squared. So everything canceled over here. I have 0. And then I have plus 2 sine squared, and then minus 2 sine. Okay, so I'm going to solve this one using a GCF as well. So I have a common 2 sine. I can factor that out. When I factor out a 2 sine, I'm left with sine. And then minus, here there's just a 1 left over. So I can set those both equal to 0. So if I take 2 sine of theta and set it equal to 0 for the first one, I can also take sine of theta minus 1 and set it equal to 0 for the second one. So here if I divide both sides by 2, I just end up with this. And here if I add 1 to both sides, I end up with this. Okay, so 0 to 360, that means we want our answers given in terms of degrees this time. So take a look. If we want sine to be equal to 0, that's going to happen right here and also right here. So 0, 360, and 180. That's my first part. And then I also want sine to be equal to 1. So that would happen right here up at the top, 90. So lots of answers for that one. All right, so last little thing, rewriting expressions using trig identities. This one we have a similar trig identity to that first Pythagorean one that we used. And this one ends up being, so remember we started with cosine squared plus sine squared equals 1. That's like our original. And then we had another one that we got by dividing everything through by x squared. We did one like that. So we ended up with 1 plus tangent squared equals secant squared. Okay, so that means this secant squared right here can be replaced with 1 plus tangent squared. Okay, so let's simplify that down. So we're looking for answers in degrees. So first distribute that 4. Okay, so I'm going to add that 7 over to the other side. So I have tangent to the 4th, and then minus 4 tangent squared. And then when I add this 7, I have negative 4 plus 7. So I get this. So now I can solve this by factoring. So when I go to factor this down into pieces, tangent to the 4th, if I put tangent squared in these two pieces right here, that would multiply out to give me tangent to the 4th. So I start by factoring like that. And then to multiply to negative 3 and add to negative 4, I would put negative 3, negative 1. All right, so set both of those pieces equal to 0, and I am almost done. So if I take tangent squared minus 3 and set that equal to 0, I can also take tangent squared minus 1 and set that equal to 0. So add the 3 to both sides and then solve by square rooting. So I want tangent is equal to plus or minus the square root of 3, and then do the same thing over here. Add the 1 to both sides and then solve by square rooting. So I end up with tangent is equal to plus or minus 1. So let's start with this one because it's actually a little bit easier. So just a tip to remember, tangent is equal to the y coordinate divided by the x coordinate. So here I want the y coordinate divided by the x coordinate to give us either positive or negative 1. So that happens when my values are the same. So this tangent would be positive 1. This tangent would be negative 1, positive 1, negative 1. So all of these values are on the unit circle, those 45-degree measurements. So this one, I get 45, 135, 225, and 315. So already 4 answers for this part. This part, plus or minus the square root of 3, I get the square root of 3 when I am in this family right here. So that if I take this value and divide it by this value, I end up with the square root of 3. So this would give me root 3. This would give me negative root 3. This would give me root 3. This would give me negative root 3. So all of these 60, 120, 240, and 300. Okay, so I ended up with 8 possible answers for this equation. All right, so that is the end.